which allows me to escape some quite harsh obligations at the end of the term. And so I really enjoy to be in Stockholm right now. Well, I've been some other places, but Stockholm is a special atmosphere, and especially in the winter. The sudden change of temperature yesterday was quite amazing. Instead of seeing dust devils out of the windows, we saw some snow devils, and kind of amazing. Okay, so my talk will be about replicator systems chemistry, and as this lecture is embedded into an astrobiology seminar, I should also come to the context of replicator research within astrobiology. And a good way to start is to start with Jerry Joyce always. This is his definition, what a minimal form of life could be, and it's a quite general definition. He sees life, and NASA followed this definition for many years, so even when the astrobiology program was called exobiology program, this was a generally accepted one, a self-sustaining chemical system capable of undergoing Darwinian evolution. The beauty about this definition is that it doesn't say anything about the structural implementation, how life, from which part it is composed. The beauty is also that it is not so simple that one can make it within the next decade. Although Jerry believed it when this definition came out. This was 91, something like this. And these were the years where the RNA in vitro evolution techniques were invented independently by Joyce, Szostak, and Turk and Gold. And so in these years, they believe that they will make it till the end of the century to come up with a self-replicating RNA molecules and an RNA replicase acting as a ribozyme on its own substrate to make copies of its own substrate. We all know that this was a dream which could not be fulfilled within 9 years, and it is still an open question how self-replicating RNA replicase could operate at all. From the historical perspective, chemists should never give a lecture on historical aspects of evolution, because basically we don't know anything. We know that our Earth was formed somewhere between 4.5 or 4.6 billions of years ago. We know that from a logical consideration that we need to stabilize the crust before we can define a hydrosphere. And we know that the early stage of the planetary system was a phase of heavy bombardment, and if you consider the kinetic energy delivered by a single meteorite impact, one should look for the phase where the bombardment ratio went down to a level that was compatible with an ancient growth of chemistry. So evaporation of the ocean is certainly a too harsh condition to sustain life, even if it's existed in these days. But from here on, we don't know anything. We don't know whether life started in an RNA world, and as the debate between Bill Schopf and Pazier about microfossils basically show, there is not good evidence that we can claim to have a fossil record of evidence of the DNA protein world 3.6 billions of years ago. This is the problem. So we are entering a gray zone, and we cannot believe in anything that is said here. We have to develop our experiments quite independent from the knowledge developed in geochemistry, hopefully, if we have some scenarios where we can create interesting chemistry, hopefully the one or the other scenario will meet with the geochemical constraints, with better models of planet formation in the future. Nevertheless, we have to explain how the molecule of life came about, and basically there are just two families of scenarios that are existing in our minds today, and one of these scenarios is certainly the soup scenario, which came up with Miller's experiment. So the building blocks of life are sugars, which combine with organic heterocycles such as adenine to form nucleotides and DNA, RNA, and of course amino acids such as glycine. And for all of these basic building blocks, we have evidence for a chemical evolution. So it is long known since 150 years, since the discovery of Butlerov, that dilute solution of formaldehyde exposed over calcium salts at pH 12 will form a mixture of sugars, however a rich mixture of sugars. And the challenge for the next generation is, of course, to learn to harvest these autocatalytic reaction networks like the Formose reaction. The Formose reaction gives you anything you want. If there are tricks, let's say dynamic or whatever, tricks to take from this Formose reaction, it's a gigantic combinatorial library if you use modern language. And the art is to harvest it into the right direction so that you can make rivals. Maybe this is a simple reaction, making glycine from the prebiotic intermediates is quite easy for a chemist, because in any prebiotic scenario we'll have the formation of aldehydes and you will have the formation of HCN. So you can do it, the Miller experiments are basically producing these intermediates, and of course if you combine it with ammonia, then you just do a Strecker reaction in this phase, and if you have more than formaldehyde, then you can generate by this mechanism a whole zoo of amino acid. And it's due to Jean-Marie Aurore, 1961, that we know today that adenine is just the product of self-constitution, where the uptake of 5 HCN molecules makes adenine, as the uptake of 5 formaldehyde molecules make ribose. The problem with the Miller scenario, the soup scenario in general, is the insight from the colleagues from the geochemical departments, according to which the early Earth did not have a reducing atmosphere. I think from a chemical point of view, all of this relates to the question whether the iron nickel core at the source of electrons sedimented fast or sedimented slow. On a slow sedimentation, you have, let's say, access to electrons in these free metals. On a fast sedimentation, there is no access to reducing equivalents. And so, according to newer models of planet formation, we had a quite fast formation of the iron nickel core. So the early Earth was not reducing, and if you start from non-reducing gases like CO2, N2, and H2, you don't get amino acids in the Miller experiments. And so this laid the cause for a change of paradigm, and the guy who saw this was Günther Vectorshäuser, who proposed another scenario of getting the electrons by the formation of pyrite from ferrous iron and sulfide iron, and by means of a metabolic autocatalytic cycle, which he called the alpha cycle, which is nothing else as the reductive citric acid cycle. So the citric acid cycle running backwards. And according to his picture, this scenario takes place under high temperature, under high pressure conditions, at the surface of Bayreuth and deep down under the ocean, in the vicinity of what we call black smokers today, hydrothermal vents. Independently on the scenario by which you form your molecules, from which you may later form a living system, sooner or later information comes into the game. What does it mean, information? To a chemist, the chemist understands information very, very simply, in a very, very simple way. To inform for a chemist means to give a thing a form, to give a thing a shape or a chemical function. And this is indeed, let's say, one line why people believe that there was an RNA world before our present biochemistry, which is based on the division of labor between DNA as the genetic material, proteins as the executive catalytic function, and RNA as a mediator molecule that translates the genetic information into an information that it can express function. So, since the discovery of the Czech and Goldman in 1983, that RNA molecules can express catalytic abilities, people believe more and more that there was an RNA world. So RNA has something to do with DNA and something to do with protein. Like DNA, it can store genetic information, and like protein, due to the fact that it has a sequence, it can fold into a two-dimensional, into a secondary structure. The secondary structure can create a three-dimensional shape, and the shape may have a function, and there are only two functions in chemistry that are interesting. One, both relate to binding. RNA molecules can bind, and then we are talking about aptamers, or they can bind to, or they can do catalytic reactions. And catalysis means binding to the transition state of a reaction, so that they can express enzyme-like activities. On the way to the constitution of the RNA world, one has to conclude that there must be pathways for the non-enzymatic copying and replication of RNA molecules. And people like Leslie Orgel several people like Leslie Orgel spent their whole life on this question, finding non-enzymatic variants of template-directed reactions. So the principle is shown here. Here's the template. What you see here, the template. So this is expanding to the 5' and here expanding to the 3', and there is a copy made on the template. And the idea is now to add, let's say, active nucleotides like this one here, which has a methylimidazole as a leaving group, to create 3', 5' phosphodiester bonds in the absence of enzymes. And to set this up, set up such a reaction, hoping that one ends at a replicating system. The replicating system was not achieved by this model, which is called the standard model in the like in physicists. Standard model, that means a one-to-one extension of building, let's say, a copy from monomolecular, or let's say from mononucleotide building blocks. This is the standard model. The standard model failed to arrive at replication due to a number of different reasons. First of all, the reason is here. First of all, it is possible to take a pyrimidine-rich template, something like C5, and to make a copy of such a template on a non-enzymatic process. But the opposite process, that means the formation of C oligos on a G template, or generally pyrimidine oligos on a purine-rich template, did not work at all. And since replication means that you need to go through both parts of the cycle, making pyrimidine-rich templates from purine-rich precursors and vice versa, the cycle could not be closed. It could be closed. What is this? Okay, so it could be closed later. So replication did not work with this standard model. The question is, what is replication in general, in chemical terminology? Let us take a look into this thing. Replication means autocatalysis plus information transfer. And there are various ways to do this. There are various ways to express information transfer. In biology, there is only one sort of information utilized, which is, from the point of chemistry, constitutional information. Sequences are constitutional isomers, but chemistry has more to offer than just varying constitution. Chemistry can play with configurational isomers, so the 3D arrangement of bonds in stereogenic units giving rise to enantiomers and diastereomers, and even chemistry can play with conformational information, of course, a long-living conformation, like a prion has a long-living conformation compared to its precursor molecule, and therefore can multiply this and transfer this information to make copies of itself by infecting precursor molecules. Okay, so in general, because I say this particularly to make aware that there are some reaction schemes on the market more recently that are sold as replication schemes, but they are not replication schemes. Replication means a transfer of chemical information, and this means making instead of breaking bonds. This thing must be more complex than the precursors. Going from simple to complex, from small to large molecules, and not vice versa. And this, of course, in a way, requires a mechanism to transfer information, and the only conceivable one is to make use of templates, molecular templating, as a means to achieve transfer of chemical information. I say this because very recently beautiful schemes came out. For example, Eric Winfrey in Science, November last year, reported on an exponential replicator based on nucleotide components. But in this case, it is a case where we start with a highly informed object, and you break it down to smaller objects that grow out catalytically. And the same is due to the scheme of Andrew Ellington, which is ingenious, where you use, let's say, circular precursors of hammerhead ribozymes, because the circles are split, so information in a way is lost. Therefore it's important to keep this in mind. Now, the earliest scheme that allowed to show that self-replication is possible in chemistry is more than 20 years old. I don't want to talk about it. I just want to show you the blueprint for it. And this is a blueprint underlying a whole generation of self-replicating systems. And the principle is quite easy. So there is a template, C, which has two colored sides, and these are recognition units. So red binds to green and green binds to red. Whatever this binding means, in whatever schemes it is implemented, it is just an assignment of sides. So A will go with the red side will go to the green part of the template, and B with the green will go to the red part of the template. And the result is then that the template is transformed into such a thermomolecular complex in which the reactive ends of A and B come together. And due to this fact, this facilitates or enables a more easy ligation of these ends to form a copy bound to the original template. Now this duplex has now to dissociate to give two single-stranded templates. And if this happens, one might expect that exponential growth is the outcome, because if you start with one template, you have another one, a new copy after the first cycle. So you could expect that if these components are in high excess of the templates, these two molecules will now produce new two molecules to make 4. 4 will go to 8, 8 to 16, 32, 68, and so on. But this is not observed in these systems. It is not observed. Exponential growth is more recently observed, yes, but it is not the general outcome, not the general rule. And the reason for it is the following. The reason is, if you compare the thermodynamic stabilities of these two complexes, you see that this one has a nick. It is composed of 3 parts, and this one is composed of 2 parts. And then, of course, it is what you expect. The complex composed of two parts is entropically more stable than the complex composed of 3 parts. And due to this higher thermodynamic stability, we have a situation that is associated with product inhibition. The more the autocatalyst is formed, the more it also inhibits. And this coexistence of autocatalysis and product inhibition in the same dynamic scenario programs a novel type of growth, autocatalytic growth, which we termed parabolic growth. And I will explain you a little bit on parabolic growth and its evolutionary implications soon. This scheme could be translated into self-replicating oligonucleotides, into small organic replicators, and even into self-replicating peptides. And we now have, I don't know, at least 1K of publications in this on this kind of replication story. Let me come back to the basic kinetics, because it is important to understand. What we can reduce the whole scheme to something like this. If A and B are the precursors and C is the template, we will have a reversible formation of thermomolecular complex, and this can be characterized by equilibrium constant, which is of course the ratio between the forward rate and the backward rate. Then we have an irreversible and rate-determining step, which is the transition from the thermomolecular complex to the template duplex. And then we have a second equilibrium, as I already mentioned, the dimerization of templates. And now let's ask what happens if we change these parameters a little bit. How do the growth profiles look like if we change this? Typically, it's not only that this is, let's say, the autocatalytic part, but typically it's also that there is a non-template dependent pathway to the formation of template molecules, so that the rate is set up by 2 terms. One is an autocatalytic part, and one an autocatalytic term, and the other one is a non-autocatalytic term. And if you look to the reaction order of the template, that means the exponent in the concentration of the template, you see that this is 1/2. And that means that the rate is proportional to the square root of the template concentration, therefore we call it square root law. And square root law gives, if you integrate the square root law, then you end in parabolic law. A more detailed look revealed 3 limit cases for such a simple reaction mechanism. The parabolic case is the one where the product inhibition is the, let's say, is the leading picture. But there are a strong exponential case and a weak exponential case, and we found this just to convince you that it's not just theory. We found an analytical expression that describes us the rate as a function of a set of variables like the stability of the thermonuclear complex and the stability of the template duplex, and also the reaction order, the exponent in the concentration as a function of these. And you see, if you compare these two 3D plots, log-log plots, then you see that there are 2 cases which have a p equal 1, that means exponential growth, but they are clearly different. These limit surfaces represent the rate laws, and they are clearly distinguishable here, although they have the same reaction order.
I forgot what is K2 again?
K2 is the equilibrium constant for the formation of the template duplex.
Right, C2.
Okay,
C2
and K1 is the equilibrium constant for the formation of the thermonuclear complex.
Yeah.
Okay. Now, this has a consequence. If you have now, we have different cases of autocatalytic growth, and this exponent p make these curves more or less explosive. The higher the p, the more explosive they are. If p is 0, then of course you don't have autocatalysis at all. And if you integrate such a rate law, then of course you see this is linear growth. If p is 1, then you have exponential growth, typical for a biological system, the green curve here. And if p is equal 1/2, it's between linear and exponential growth. And this is parabolic growth, because if you integrate it, you see that the concentration grows with the square of the time, like in a parabola y equals x squared, where let's say the y also follows the square of x. Now, of course, there is the case of hyperbolic growth, and hyperbolic growth is so far has been not observed in true experimental systems, but I should, let's say, at least mention that there are also cases of higher order autocatalysis. Now, parabolic growth has now consequences for the evolutionary capacity. Just imagine a Gedanken experiment to make it as easy as possible. Just consider a flow reactor in which these precursors of templates flow in, and you have 2 or more templates that are formed by parallel reactions from the same precursors. So these 2 templates compete for the incorporation of building blocks, and then one of many different things can happen. The strongest replicator, so the one with the highest feedback, may supersede the whole reaction chamber, finally surviving as the only competitor in such a compartment. And then this is equivalent to Darwinian selection. Or the faster replicator is not able to push away the weaker competitor from the common resources, and then this is equivalent to what biology describes as coexistence. Now the growth, the explosiveness of autocatalytic growth determines whether we are ending in a Darwinian situation, whether we are ending in a selection, or in the case of coexistence. This was unclear since a number of years, and there was a debate between Eigen and Schuster on one side and Urshad Mario on the other, but I think it's clearly safe to say that for such reactions occurring without further coupling of C1 and C2 formation on decay, it's a fair statement that parabolic growth will result in coexistence, although at enhanced selectivity when compared to non-autocatalytic growth at all.
But isn't this obvious? I mean, why does this require Eigen, with his genius? Because if you've got two things competing for a limited resource, the resource has to be limited. Otherwise the whole thing doesn't make any sense.
Right.
If you've got two things competing for a limited resource,
it's always replenished.
Yeah. If you have two things, it's replenished. If it's replenished too quickly, that'll destroy the model, won't it?
No. I mean, these will grow. Of course, I mean, you may adjust the flow rate in such a way that there is no chance to grow at all. Then, of course.
No, but I mean, if you make the resource, I see. If you make the resource that way, but isn't it clear that if you have one of these guys growing exponentially, it has to be at the cost of it. I mean, it just seems like the quicker one is growing, the more likely it's going to take over.
Now, let's say the quality of
growth is much faster than
the quality of growth has no direct relationship to the rate of growth. I mean, you could imagine that you have fast parabolic growth and slow exponential growth that there is one replicator which grows exponentially, but let's say at a lower rate constant, and one replicator which grows only parabolically at a faster rate constant. If you wait for a long time, then the slow exponential replicator will push about it.
Well, but the reason for that is that the exponential growth will produce more of that type more quickly, so that there'll be more of them growing.
It depends on the phase of replication, where you are. Let's say this is a matter of dynamics. Let me show you some examples later on the computer. Let's say here in this case, only replicators of the same type of growth are compared. Okay, so two replicators, both parabolic, will coexist, and two replicators, both exponential, will invariably result in selection. And this was not so clear as it is obviously to you, and it was even not clear.
Maybe I don't understand. Does exponential growth has to do with the number of organisms or the number of chemicals that are being produced per unit time?
Yeah.
That's what it's all about, isn't it? That in exponential growth, it's like some kind of geometric progression.
Exactly.
Is that what it is?
Yeah, it is.
Okay, well then it does seem obvious, because in exponential growth, you're starting out with a few, and you rapidly produce large numbers of them. So even if each one...
But also for parabolic growth, even if you have, let's say, a parabolic explosion, you will rapidly produce a large number. This is a qualitative statement, let's say, but the degree of explosiveness determines, let's say, the outcome. And if you look to the evolutionary consequence of p equals 2, Donna claims that due to the fact that she has these bimolecular species, that there is some evidence for hyperbolic part in their kinetic, then the outcome is the survival of the last common. And if it's in a chiral symmetry breaking situation, the outcome is the survival of the last common chiral impurity.
All right, well, you can ignore me now. We don't go later.
No, but let's say I found it to be that these fundamental things need to be remembered very, very often, and because it's really they are guiding the games of replicated.
But isn't it a point? I mean, isn't like in a laser, I mean, you have laser modes and one
Yeah.
will take over and it kills everything else.
Yeah, in a sense, a laser mode is a perfect analogon of a Darwinian behavior, because all the others, which are not under the constraint of being parallel, or let's say orthogonal to the two planes, will die out. Well, even if they, yeah, yes, in a way, it's a selection mode, and.
So why, but historically again, why was there, what did Eigen and Schuster say? Why? They said
If you
they didn't believe
read
that.
Eigen and Schuster wrote, in general, if the reaction order is defined by a term xi with the
Yeah.
power of p is the autophyletic exponent, the reaction order. Darwinian behavior may be found for an exponent of p larger than 0 or smaller or equal to 1.
Yes.
So from 0.001 to 0.99 or including 1, it's always Darwinian. For p equals 0, only for p equals 0, only if p is, there's no autocatalysis at all, coexistence would result in a growth-limited system. And this was contradicted by Zachmary, who said that we shall show that while the last sentence of the quotation is true, this one here is true, the last but one is not. This one here is not, is wrong. Sub-exponential growth invariably results in coexistence. So if the reaction order is 0.9, it will end in coexistence. If it's 0.99, only if it's 1, it is selection. And this is...
So in the example of a laser, we don't have such a thing. Isn't that right? We only have exponential growth. Yeah, and therefore that is actually doesn't have a counterpart in physics, mostly. I mean, not at least in those examples. It was unexplored in that sense.
Yeah, let's say, but in a way, let's say you have laser is a selection, is a Darwinian selection.
There is no disagreement, or there was nothing.
But we don't have parabolic lasing.
No.
We don't have hyperbolic lasing.
Certainly not.
But let me just remind you, and this is also relating to Schneer-Lifson, because Schneer came up, although Zachmary and a mathematician in Oxford, I forgot his name, they found a Lyapunov function proving the global stability, that global validity, that parabolic growth invariably results in coexistence. And then Schneer-Lifson came up a little bit later, after I showed this movie in Berlin, that if two replicators grow and at the same time are decomposed, I see that, okay. So if C1 grows from A and B, then C2 grows from A and B in an alternative way, and both are decomposed to give, let's say, X1 and X2, then in such a system you can still have selection. So if you mix it up with a consecutive decay of replicators, not only the flow out as I showed you, then you have conditions for doing Darwinian chemistry again. And we found if you mix it, in this model, if you do the replication on a surface instead of in free solution, overlaying the replication event with surface binding, you also are able to develop Darwinian behavior. This is what we call the chromatographized replicator model. Okay, but of course we are not. We ask the question: is it possible to arrive at exponential replication if you increase the dynamic complexity of the system? So, working with two interwoven cycles instead of with one cycle. The answer is no, it is not possible. You can have networks of replicators. 93 more recent examples from Reza Gadir and Gohn and Ashkenazi, and they basically arrive at the same conclusion. It's not possible to create miracles out of increasing the complexity. The fundamental things are always showing up in the very, very easy, simple systems. If you create, let's say, more and more cycles, this may look more and more impressive, but it doesn't give any clue to the origin of Darwinian behavior. You can create exponential growth by applying, let's say, stepwise iterative games, like what we did here is surface-promoted replication, exponential amplification of linear mimics, where spread, where you use a surface and a template, and you stick the template to the surface, and then you switch the conditions. Under the new conditions, the template, these yellow arrowheads will not go to holes in the surface, but because the holes are filled in a way, but they can hybridize with a template, and you can run ligation chemistry, form a copy of it, and then of course you change the condition again, the copy is released from the immobilized template, and under these new conditions the template can be immobilized so that the surface keeps things together, keeps things apart from dimerizing. Of course, if it's too densely populated, it will not work, but let's say under the window of condition we applied, it will. This is a scheme which has no prebiotic relevance because it's not an autonomous scheme of replication, but it has a nice application in the field of nanotechnology and can be combined with a game we call chemical copying of connectivity. The idea is to have information not only in linear molecules but in branch molecules, and if you can copy the connectivity of these branches, then you are principally able to copy nano objects formed from such tris oligonucleotides as the DNA dodecahedron which will come out in Angewandte is just accepted in 2008. But this is just looking for new ways of doing molecular replication has some value not only for prebiotic stories, but also for those who are interested in nanotechnology. Now let's go to the more fundamental things. Don't look, just listen, because I will show you this plot again, and this plot predicted that it is possible to make an exponential replicator. This was 93, and we didn't make it. We were keen to make it experimentally, but another lab was faster than us. It was the old Ian Sutherland in Manchester. He found the first example for a supraparabolic, still super-exponential, but supraparabolic replicator in a very, very primitive reaction compared to the complexity of nucleic acid reactions. Just a simple Diels-Alder reaction 10 years ago or 11 years ago, the Diels-Alder reaction between a diene which carried a recognition unit in the dienophile file carrying a recognition unit, and he found that the P in this case is 0.8, so this is close to 1. And this, of course, triggered to why is this such a great replicator? And this is why we put some own efforts into this chemistry, and we minimalized replicators based on the one Sutherland one. This is an even more simple replicator where the recognition units are simplified. And what we found here was kind of interesting. So it's the same story like in this blue-green color game. You have two building blocks, and they can bind to a reaction product as a template to make a thermomolecular complex, and then the thermomolecular complex, the reaction takes place in the thermomolecular complex, which is here, ABC, and the game can continue. What we found here are some kind of bizarre NMR phenomena when we look to the reaction, and this is what I would like to talk about today, because it has been shown by now in many other cases as well, that if you look to these dynamic kinetic shift-shifting phenomena, you can, if you are able to read this information about the dynamic shifting of NMR signal, you can extract much more information than without. The paper is was published in JACS last year, and this is the phenomenon I mean, that the signals in the NMR belonging to certain protons here do not only increase their integrals, but do show a shift change as a function of the time.
What is the time scale for this shift? Oh, you have it.
Okay, move 0 to 17 hours. Here you see an example. What you expect for such a molecule is, of course, that for an autokinetic growth of such a molecule, measured by these two protons on an olefinic bridge, is that the integrals show an induction period, so not very much integral here, but they do show this strange shift-shifting. So they change, the peak maximum changes as a function of the time. And this is not only in this case, it's not an isolated phenomenon. You can play a lot of games with modifications. For example, if you compare the R enantiomer of this compound with the racemate of this compound in its reaction with its malonimate, you see that in one case they shift to the same side, here they shift to different sides. You can also follow this at the methyl groups here of the bizarre changes and shifts. Those who are doing NMR spectroscopy and did not see this before, I mean, it was bizarre. This impression was bizarre to us as well. You can create mixed situation here. Lots of other, and it's not only working in the case of replicators. If you look to the SOI reaction or workhorse in nonlinear Carrel symmetry breaking, you see this shift-shifting as well. So what the hell is shift-shifting? How comes it all about? In order to understand it, one has to go back and to remind oneself to the uncertainty principle of Heisenberg. The uncertainty of the energy multiplied the uncertainty of the time is the Planck constant divided by 2 pi. Or if you remind the Planck equation, if you replace the energy, you see that you can reduce this uncertainty principle to something which is quite easy to understand. The uncertainty of frequency and the uncertainty of the time for a periodic process has to relate, let's say, to a unity side passing through the. This means simply, if you want to detect a periodic signal, you have to run through the cycle for a certain amount of time in order to detect the frequency quite safely. If you don't do this, and you have the problem that it's too short, if it doesn't repeat in the time when you observe, then you have no idea about the frequency of the system. And this can be translated now into the NMR time scale, just by replacing the uncertainty of the frequency into an uncertainty of chemical shifts and the ground frequency of the instrument. And then you see that, well, I mean, you have to observe the dynamic phenomenon for a certain time in order to see it. If the phenomenon, if the signal does not, if you want to have a stable signal, let's say at a given chemical shift, then the system should not escape from its observability by internal dynamics. So, for example, if you have an observer complex AB, which is composed of A and B molecules, then the rate, then if you want to see, let's say, the complex, either it has to be ultra stable, or the decomposition rate must be larger than the difference between the complex AB and its components A and B multiplied by the ground frequency. For example, if you have a delta of 0.1 ppm and you measure at 600 megahertz rapid exchange leading to a fast decomposition of the complex, and to shifting occurs if this complex decomposes faster than 60 per second. So you can just, from the ground frequency of your experiment, of your spectrometer, you can, let's say, roughly determine how fast the process of internal recalibration must be in order to see the shift.
I don't understand the first line. I mean, you have a quantum system and you have a certain energy system. And you have uncertainty in the energy of the quantum system related to an uncertainty in the how long time it takes for that system to change, which is delta T. And then you just switch over to something which is h times nu, which is a frequency. I mean, I can understand for an electromagnetic.
Well, I mean, you can certainly translate an uncertainty into the energy to the uncertainty of the frequency, which belongs to this energy. Don't you think so? This is the trick I employed here, and everybody who is involved in dynamic NMR tries to get an idea about dynamic phenomena by applying this trick. Although it looks bizarre, I agree at the first glance.
I mean, h nu for this is the relation you're using to get.
Yes, exactly. The Planck equation.
What is the problem? I mean, we are just talking about actually the problem about
the uncertainty of the energy.
We just
somehow relates.
We don't really, and that's the.
No, but how do we know? How can we say that the energy in just this particular case is equal to h nu? Is that obvious?
Is that what it is actually?
Now the delta stands for uncertainty, not for difference of
but you
and now you replace, you translate the uncertainty of the energy into an uncertainty of the frequency.
Yes, but you
by applying the Planck equation.
Yeah, but the uncertainty is on the delta. It's delta. It's important, not the nu.
Alright. Of course, it's the delta E, but you translate it into an uncertain frequency. But I was just wondering, is it obvious that the energy of this quantum system can be equal to h nu? Is that obvious?
Well, if you go I mean, I would say that this is not even limited to quantum system, but to any periodic system. If you want to observe something periodic, you have to wait for a certain time. If the observation time is too short, you will not get. If the system is not able to go through one cycle at least, then you don't have an idea that this is a periodic system.
I have to think about this, so go on.
I mean, maybe the trouble was that you actually talked about Heisenberg uncertainty principle. If you just talked about Fourier transform, you would be happy, maybe, right? If you never mentioned, yeah. If you, yeah. So he was
Maybe that this relates to Heisenberg.
It does, of course, yeah. But that causes extra confusion, perhaps.
So give me a hint what I should do. I mean, this is the.
Remove the first.
No, I don't want to stop here. Please go on.
Okay. So now let me remind you that NMR, we call this the extraction of, let's say, the kinetic modeling of these shifting information. We call this kinetic NMR titration. And this contains titration, and of course classical NMR titration is very often employed to determine the thermodynamic stability of supramolecular complexes. And the way it is done is that you just take one of these reactants and put it into an NMR tube, and now you change the concentration of the second component, and you observe a change of the chemical shift as a function of the time, as a function of the molar ratio between these two. But it is defined in an equilibrium situation. So from this data, you vary AB, the ratio between the reactants. You measure the chemical shift change occurring by this AB variation. Feed data to the corresponding equation, which describes the observable chemical shift as a function of the concentration of the two partners. Get the complex formation constant, the equilibrium constant, repeat the whole at various temperatures, and by this, from front of an Arrhenius analysis, you get delta H, delta S, and so on. Then you have a thermodynamic description of the system.
So you're proposing this is the normal expectation.
This is the normal way of harvesting shift changes in NMR.
You're ascribing the time dependence of your shift change.
Exactly. So this is what I would like to make sure. The only tiny invention of the whole story is that while this one is time independent, time invariant, now we can think about a time variant, a time dependent solution of the whole. So if you have the chemical shift observable as a function of the time, then you can basically write down the same equation as is written down in order to derive the titration equation in the classical case. So we did so since the mole fraction is time dependent. The mole fraction can be computed by the simulation. If you have all concentration of the species, then of course you have the mole fraction of the species. And then you can, let's say, solve the story. What is the advantage of kinetic NMR titration? It links structural and colligative information. Because the shift themselves is a structural information. And it is relatable to quantum QM and QD methods, where you can, let's say, estimate the chemical shift if you don't know the shift of the proton, because this is a fit parameter also. If you don't have any idea about the shift of the proton in a complex, you cannot measure this. because it would have to overpopulate it, but you can only, let's say, have a limited range of concentration where you can play with it in an experiment, then you can compute it. And so this is structural information that can be obtained by computation, for example. And of course the mole fraction with or without time dependence is colligative information. It depends on the number of particles in your system. And
so what's changing? Something's got to be, one of those has to change with time.
Yeah, the mole fraction changes as a function of the time. In any kinetic situation, the ratio between, let's say, compound A and the sum of some other compound changes as a function of the time. This is typical kinetic, and this consideration from the Heisenberg gives you the window of rate constants for the rapid equilibria you have to consider in order to apply these methods. Now let me show you how simple it is. Okay, so here you see again the two protons developing as a function of the time. Let's do an actual simulation. Let's fit these changes of integrals and shifts as a function of the time with respect to a reaction model of a replicator. I have to wear my glasses now because...
You want to share?
No, so let me just... No, Axel, it's really very polite, but... so what you write down, somehow, is the reaction model. You see there's a typical replicator. You have the transformation of the thermonuclear complex to a template duplex. You have the formation of AB, because red is complementary to green, so red and green should interact at the level of the precursor molecules, and also should interact at the level of the template. A plus C gives AC, BC, BC, C plus B gives ABC, BC plus A gives ABC, and the template should dimerize. And some of these rate constants and equilibrium constants are known, or let's say you can have at least a reasonable idea where they are, and some of them are not known. So here, for example, for the supramolecular association processes, you may think about diffusion limit, which is perhaps a little bit faster than the 10 to the 7, but it doesn't matter because you are interested in the equilibrium constant and not in the absolute rate of the backward reaction. And then there are some others, and a good approximation, for example, is to assume that all red-green interactions, at least the first order approximation, are equal. Whether a green, let's say they have all the same shade, all the same, if a green kisses a red particle, then the red particle may be involved in some other maybe part of another molecule, or it may react as an individual particle. But let's say the interaction gained by delta H, delta S gained in this process should be roughly the same. So they should do it with roughly the same efficiency. And well, you can test such hypotheses, for example, by just looking to the data. Here you see the actual simulation, you see the RMS, you see how the shift change now comes about. Here you see the RMS again, you have the energy profile, you have the RMS again. And what comes out from this simulation is then the rate equation. You don't never do it manually, please. If you are, I see lots of kinetic papers with a huge complex dynamic model, and I routinely reject this as a referee because, I mean, it's painful to recode the reaction equation and really understand as a chemist from the differential equations, right? So if someone comes up with a set of differential equation, not giving the reaction model behind, this needs to be punished, in my eyes, because it's routinely, it can be translated routinely, and there is no need to impress referees or to cause extra work to referees. This is my severe. Okay, so you get what you want, and then you have to explain. You have numbers, and these numbers can now go through temperature-dependent processing, so that you arrive at an energy profile, delta S, delta H, for the different steps of the replication involved, and then you have to see how this experimental energy profile can be compared to a theoretical profile. Now, luckily, computational chemistry is quite advanced today, so you can consider first different pathways. For example, these in a racemic situation, these cyclohexadiene units may be R-configured, S-configured, so the templates may have an autocatalytic pathway or a cross-catalytic pathway. You can compute all this on various levels of precision, or here, for example, with the density functional theory, and then you can compare it, and you're finally happy, do more and more experiments, and the reason why this is a good exponential replicator is the following. Everything in life is either concave or convex, Vladimir Krylov. Let's assume that these molecules are not straight, but have a conformational distortion showing up as a convex surface. Right? The convex surface will enable a perfect binding of A and B to form this termomolecular complex, and the transition state of the Diels-Alder reaction has a little bit longer bonds than the ground state. So this can still react, but after the reaction you have a new geometrical constraint, so causing a kind of distortion. And you can look to these different cases in the computer model, and this decomposes faster than it were possible if the template were just a straight story. So this is the way how to understand replication by the conjunction of computational kinetic studies, NMR studies, and so on and so far. And in a way, it's boring on a symposium about homochirality, because although there are some stereochemical features of these systems, it is not a good example for a chiral symmetry breaking process. But let me show you something which came up in the formation of a new coast action on systems chemistry. You know Donna Blackmon, certainly. She's the expert of chiral symmetry breaking, at least for the case of the Suai reaction, and in some other cases as well. And she is challenged by an even more beautiful chemistry developed by Svetlana Tsogaeva in Erlangen, and this is the chemistry. Svetlana claims that this reaction, the addition of the enol of acetone to the imine from ethyl glyoxylate, Albert Eschenmoser, hello, glyoxylate scenario, and the paramethoxyaniline, so a Mannich type reaction, is autocatalyzed, and she explains it by assuming replication type of picture, so that this acts as a template expressing hydrogen bonds to the PNP imine and thus accelerating the reaction. I don't believe that weak hydrogen bonds This one here, just imagine if you have a dimer instead of polymer. No cooperativity at all. Do you agree? Yes, I'm sure. So I don't think that this really tells a story. And so we were keen to find out what is this reaction all about. And then a little bit later, in September last year, she claimed in a paper which is a seminal paper, the most seminal paper published in the field since Kenzo Zoai's work 15 years ago, and at least in my opinion, demonstration of spontaneous chiral symmetry breaking in asymmetric manic and aldol reactions. And this is my hero. This is the hero in my group, Matthias Pankau. He's a brilliant chemist. And he said, when he read this claim, if this is true, I will eat the stem of a wisher. In Germany, you know, fresse ich einen Besenstiel. It's hard to translate. Axel, help me, please. The stem of a wisher, that means it's something which is quite, it's difficult to eat a stem of a wisher. So the group does not anymore doubt this statement. He has to eat the stem of the wisher, but we will make it easier to him because we may decide to use chocolate as the material of the wisher stem. So what was the claim of? This was the claim. The reaction of acetone plus this PMPamine in the absence of a chiral information, no proline, no whatsoever, gives a non-racemic product. She found this by analyzing the composition of RNAs as a function of different reaction conditions. So she always waited for 1 day or something, or sometimes 3 days. And so we said, well, I mean, if this is true, we should see chiral symmetry breaking, the kinetics of chiral symmetry breaking, if we put these chemicals into a polar emitter tube. And we did so, and here you see how alpha, the optical rotation, changes as a function of the time. There is a clear induction period, nothing happens over the first 200 or so minutes in this similar examples. And then you have, let's say, this transition. And if you repeat the experiment, so far we have done it 10 times, you will find the following. If you add all this, sometimes it has a short induction period, sometimes it has a long induction period. Sometimes it goes negative, sometimes it does not anymore, let's say, end at the same amplification level. But if you do it as follows, if you take this experiment, put it into a tube, and wait for 24 hours, then take 10% in the next one, wait for 24 hours, then 10% in the next one, repeat it all over again, so apply what was named a serial transfer experiment by Spiegelman for the evolution of RNA molecules, then you end up at this constant level. We were able to follow the reaction by NMR.
Excuse me, when you did it 10 times, was the average of all 10, or if you did it 100 times, then better? Did it average out to 0?
Yeah, I mean, not exactly 0, because we just did it
we
found this case more often than this one so far. But, I mean, from 10 you will not say...
No, but it started to go to the average.
Yeah, so it goes into the direction you expect, okay.
Yeah, but by going from one to the next tube and stuff like this, shouldn't you reach 100%?
I mean, this is December 2007. You know, September was her claim, then we immediately started to look what's going on. So we can confirm her reaction. And
it's an interesting thing, but it's really a little bit like the sodium chloride crystallization.
No.
I think so.
No, because a real stereogenic unit is involved.
I know, I understand, but phenomenologically, in the sodium chloride crystallization, when you start at the proper rate, there's an initial the initial seed has to be left or right-handed because of the nature of the crystal.
Yes.
And that then acts to cause the rest of the crystal to follow that. I'm sorry? There, yeah, okay. And that's what's going on here. Here, there's a very slow initiation, which has to take a choice of left or right.
On which mechanism? I mean, in the case of the crystallization.
The mechanism is completely different, but the phenomenon is the same. It's a seed that's constrained by the nature of the system to have to be left or right, and the system is moving so slowly in the beginning that there are not enough of these seeds to make an average of left and right-handed seeds of equal content. And therefore, whichever seed is in excess to begin controls the system. In that sense, it's phenomenologically related to the sodium reaction.
Okay, so
Phenomenologically, it is also related to the SOI reaction.
it is SOI reaction. It is, let's say, what is the difference between this reaction and the SOI reaction? If you think about, really think about in terms of prebiotic chemistry, this reaction has much more potential. Why? Because the involvement of aldol and Mannich type reactions.
What is the solvent?
Well, we take acetonitrile as a solvent here. So, but the concentration are quite high, so it's much higher than in the replicator system.
Who did this, by the way? So what's her name?
Soeva.
Where does she work?
In Erlangen.
In Erlangen?
Yeah. So, I think it's an important contribution. And this is our hypothesis.
That's where Schleier went.
More, a little bit more.
Back, but that's where Schleier went.
This is, I think, the mechanism. So no replication, but what we would like to call metabolic autocatalysis. Very similar to the foremost reaction, where you have this involvement of glycolaldehyde, adding formaldehyde to make glycerol-aldehyde, making an indiolate isomerization to produce dihydroxyacetone, adding another formaldehyde to make keto aldolate, keto-aldol tetrose, and then aldotetrose, and then it's split into two different autocatalysts. The difference here, this is why it's new and exciting, in the foremost case. In the foremost case, if you break down chiral,
In which case?
in the foremost reaction case, you know, should I? Oh, I'm sorry.
I don't know what's the format.
Everybody in this field appreciates the format. Should I get one? Just the wish one. Yes. Ah, okay. Okay, the foremost reaction. Just for colleagues.
We have a conspiracy here against you. We have a conspiracy against you.
Really?
Yes, absolutely.
Why?
You don't believe in plastic. I'm sorry, go on.
You still say that was the replication. No, I'm almost.
That's why may I ask what the solvent was?
Yeah. Acetonitrile, please do me the favor, create weak hydrogen bonds in the acetonitrile. You can also add some methadone here, please. This is almost impossible. So the foremost reaction, you have the chiral molecule, this aldotetrose, undergoing whatever isomer it is right now, a retroaldol reaction to form two molecules of CH2, OH, CH2, glycolaldehyde. That means that the generation of the autocatalyst is coupled to a destruction of chiral information. Right? And this is different from the reaction here, because here you have, let's say, something. If I go back to the mechanism, we believe that the following mechanism: the Mannich product is not acting as a non-covalent, as a supramolecular template, but as a kind of substrate, or a reactant. So it reacts, this is a secondary amine, reacts with the acetone to form this aminal. This may then end in, let's say, a cyclic compound. Or it may also split off water to form the aminium salt. The aminium salt may undergo isomerization to form the enamine. Once the enamine is formed, it will much faster react than acetone itself with a PMP amine. And then you have something like a dimer. This may be S, this may be S, this may be R, and so you have all different situation. And you have, let's say, dimers at at least two different levels. At the level of the aminium salt and at the level of the hydrated aminium salt. And so you have, let's say, at least two different layers to define differential stability in the context of a rank. You can do it kinetically and thermodynamically. This is the advantage in this system. And then, of course, it has to split. And if this splits, there will be a difference between, let's say, splitting of RS, but also concerning the synthesis of these compounds. So this is the mechanism we believe is underlying the reaction scheme. No replication at all, but a case of metabolic autocatalysis. And we have evidence for NMR evidence for the involvement of such enamine. The NMR evidence is not the strongest one because we are dealing, I have to say this, if we look to the imine, to the metoxic signals of the PNP imine, we look to these signals, these are sharp singulars. We see 17 to 19, depending on who one counts. 17 to 19 different signals. So this is a beast of reaction. It's not a clean reaction. I have somehow arrived at the idea that metabolic reactions, like in the human body, have to be complex to arrive at dynamically interesting signatures. Okay.
Now, what are the compounds that you think are responsible for the rotation? Everyone, all of them? Do you have an idea about which are the molecules which are forming nexus? Which enantiomers, which molecules are forming nexus?
Well, the problem is the following here. If you work with Mannich chemistry, you usually work up. And during work up, all the stuff is splitting down to the Mannich base. So if you isolate it and purify it, you end at the Mannich base. It arrives at something like 25% yield, 30% yield, something like this. But this is not the whole story, because the reaction after chromatographic workup is different from the picture you see in the NMR in situ. And you can only count on what is NMR situ, and NMR is less than 20%. There are lots of, let's say, the Mannich products, we can see it, yes, but it's less than 20%.
So if you contaminate your system with the Mannich product,
we did
contaminate it in one direction?
We did this serial transfer experiment to arrive at a stationary chirality. Now, concerning the serial transfer experiment, I think we have a nice machine in the design of a nice machine for this to prove it more conveniently. We call this procedure pulse ignition flow feedback, PIF. One may call it molecular heartbeat, or one may call it Kemp Plumber's pulse gun, or chemical laser if one want to hype it somewhere. But let's forget about hyping, this is just a joke. In any case, one is invited to look to such reaction like a doctor looks to a patient who just suffered a stroke. What can happen here? It can happen exactly like this, and then the system works. What is the defibrillator of the whole? Think about the following arrangement. An HPLC type of arrangement, in which you have, for example, solvatorous reagents, acetone on one class and this PMP amine on the other. And you have, let's say, an HPLC injector before the mixer where you can pulse in proline, or any kind of other chemical, chirochemical, that interferes with the reaction system and causes a bias to the system. What will happen? The proline will react with this acetone in this mixer, creating a plug flow, a plug that flows through the whole reaction. And after at the end of the column, 90% leaves the column F from the detector, and 10% is pumped back. And now what's happening is the following. If you look to the simulation, the following is, this is the proline pulse, it goes out, and now, this is now the autocatalyst. You see, after the defibrillator has started to work, the molecular heartbeat beats again, it's chirality transferred to the beginning. So it's a flow setup of a serial transfer experiment, ending in a periodic oscillation with although the mechanism behind this reaction is simple autocatalysis. And I think this is also for prebiotic chemistry somehow translatable principle, because flow feedback replaces the need of higher order autocatalysis or Lotka-Volterra dynamics for oscillatory outcome. If you want to create a chemical oscillator, you may either go the vacillator of Ilya-Prigogine or variants. Here you have a 2A3X situation, so hyperbolic autocatalysis, which is heavy to achieve in real chemistry. At least it's not predictable. You cannot design a 2A3X system very easily. This is very important. Or you have to rely on Lotka-Volterra dynamics, predator-prey dynamics to create oscillatory output. But if you take such a flow network, the continuous reflow, you can create oscillation without any miracles, just based on the flow feedback principle. And this is the beauty of autocatalysis. An autocatalyst is a catalyst and at the same time a product of the reaction. So if you harvest the product and feed it back to the beginning of the reaction, it will have an effect. And this is now here showing up as oscillation. We have shown it experimentally, not in a very nice demonstrable way, by the permanganate oxidation of oxalate. It works, so you see periodic changes of the permanganate color, but it dies out in 3 cycles, and the reason is that we don't have a plug flow machine so far. We have a laminar flow. It was done by peristaltic pumps and tubings as a reaction vessel. And of course, if you don't have material that causes turbulent flow, plug flow, then you have laminar flow, and then the peak gets too fast to go. Okay. Well, thanks. That's it.
Thanks, Gunnar, for your impressive presentation and achievements. Questions, please.
This last example is not a reminder about the separation of, if you take a non-racemic mixture and you run it in a cycle, you can separate between the racemate and the non-racemic. This has been reported actually a long time ago. That if you take such a system which is non-racemic and you just put it through a flow to the column, you can separate between the two non-racemics, even if the column is not covered.
you know, that was done by
And this was done because this happens because the DR actually can interact.
because you get diastereomeric complexes. It was also done in Switzerland too.
Yeah, by driving.
Yeah, by driving. Yeah, that's right.
Let's say maybe that this is reflow has been especially interesting. Reflow is in the context of autocatalysis. Reflow, usually in industrial chemistry, is used to have a better economy, efficiency of the whole process. So what they do is they recycle the precursors that have not been reacted, so that they have a better conversion of precursors. But in this case, the product is recycled and has a completely different meaning. You see, what you see is that something grows up, and then if you have now a change in the composition of this, something grows up, like RS ratio, for example, you are expected to drive the system to the stationary state of where it should end, if you consider fixed point analysis and such things.
What about trying to do this experiment with chiral shift reagents to try to differentiate maybe between some of the antibodies?
Yeah, this is what she did. Let's say chiral shift, adding chiral shift information, relating, but she did it at the level of separated dynamic products. So where everything is clear, this signal belongs to this protein, and so. But here, if we look, you cannot add chiral shift to this mixture. I can show you the full, because you have to. This is the problem. What we are right now doing is to test this DOSI technique, diffusion ordered NMR spectroscopy, so that you can. This is a kind of NMR two-dimensional technique that allows you to separate different species, components of a mixture. As a function of the diffusion coefficient of the different components. So this, we expect that this will help us to analyze the system, which is beastie. It's not a clean reaction like a self-replicating system.
But in principle, you can simplify the system. You can simplify the system by labeling some of the hydrogens with deuterium, and then to fix in one of these, so one of the groups, and then by this method you might be able to monitor the formation of the various products and to see what is the non-numeric axis of each one of the products which is forming the product.
You're right. Mark?
Well, that person in Erlangen, did that. So does that suggest that if Kenzo Soai, if he ran his system without putting any of his miraculously minute chiral bias elements in there, would end up with a similar result?
This experiment was done.
He did it.
Yeah. And he got it the same way, like that. He makes
same as her. Yeah. Which so you're dealing with them.
And then he was arguing, and I think also there was somebody else.
I don't know. I mean,
Kenzo
recently started to look to kinetics. But
No, I'm speaking about the product distribution also.
Forget about the kinetics.
Singleton also did that. 66 experiments, starting from pure resonance.
Yeah.
And then you got 26 in one direction and 26 in the other.
All that's necessary for this is a very slow beginning and some sort of a catalytic, some sort of an autocatalytic process. A very slow beginning and an autocatalytic process is all you need.
Yeah, it's slow. Let me show you why it's slow. We have a slow and a fast thing. This here is slow because the equilibrium between the enol of acetone is completely at the level of acetone, 10 to the 8. And the rate of conversion of acetone to the enol depends on protons. If there are no protons, and in the beginning there are no protons, this is a slow process. So the reaction cannot happen, and once you have the first autocatalyst, however, it itself continues.
So the whole thing becomes, in the end, quite simple and quite beautiful. That the whole thing is simply a matter of, there'll be many cases of this found now. The door has been wide open.
Yes.
Well, in fact,
This
we're able
is
to design.
for the experimentalist. This is Klondike.
No doubt.
This is, your organocatalysis was Klondike 1.
Yeah.
This will become Klondike 2. I bet on it. If I would have money and to burn on a, let's say, expectation, I would say put all the money in this direction.
So you won't get to eat the chocolate.
But I think what is surprising at least for me, that all the previous absolute asymmetric transformations require the formation of some kind of cluster. And not what you're describing here. You're describing an example where you can generate an absolute asymmetric synthesis based on a single
You
molecule.
don't need the clustering. See, the clustering plays the role of the autocatalysis.
Yeah.
It's exactly the same thing is going on, except, it's a different mechanism. In certain cases, like the sodium chlorate, you get a cluster. The cluster is the beginning of a crystal growth. That then sets the stage for what
We have a dimerization in any case, so it's
you don't need a clustering here. Clustering is not necessary
but I
because
mean, that's
here,
the analogous thing, simply. I mean,
It just has some kind of supramolecular structure, maybe dimer or something more. But here, what I find fascinating here,
Because you have
if you take a single molecule and the probability to get reaction with one molecule and another molecule, then it's quite identical. So the question is, in other words, what you're doing here is you're amplifying the fluctuation from the racemic state, like in this Suai reaction.
No,
they were considering it.
But Mayor, look, when you first get the first reaction,
Yeah.
if this is slow enough,
Yeah.
you're going to produce so few of those molecules in solution at any time that you can't have a racemic mixture. You don't have enough.
No, racemic mixture is not stable, doesn't exist. Always you have a fluctuation of 10 to the 12 molecules.
That's right. So in the
And
beginning,
the question is how whether these 10 to the 12 molecules are sufficient to preserve that you can preserve that information. And
Well, it is not, interestingly, it is not a second order case. You see it both from this curve. This looks typically exponential and not, let's say, more than this. You can, fit it to an exponential. So it is presumably not something where you need two products to make a third or a fourth, so no clustering at all. It is then, I would say, it's a Frank type model where the differential stabilities or the differential rate of formation and decomposition of these two species here determine the rest. And I leave it open here.
as long as that's very fast compared to the reaction that forms the first chiral material.
Yeah.
Because then what happens is you form that first chiral material necessarily not in a racemic state
The
because
question is how many molecules you have to create,
well, this
how
is
much you have to generate in excess.
it's a detail. This is a detail that Gunther can work out. But you're producing so few of those initial chiral molecules, and immediately off they go. And there's so few of them that they can't be racemic. There's got to be an excess of
The
one over
first
the other.
molecule go on, and then you have the second class coming out, which can be opposite to the first one, unless you have somehow transfer of information from the first one to the next one.
But you do go back. You have a cycle going back.
It's really like in the foremost reaction. When you build, let's say you take this one as an autocatalyst, add formaldehyde, you get a C3 unit, so glycerolaldehyde. Then you add another 3 unit, C4 unit, and the C4 unit splits into a 2C unit.
Just a minute. Look, the answer to that, look, you'll get very few of these, right? So they go quickly to here. So this is already not racemic because there's too few of them.
No. This is the excess component.
No, I understand. But then when you get to here, when you get to here, you can go back to here but without having to come from here. So you can produce a lot of this stuff.
I mean, yeah, but Mark, just Mark me here, please listen in this case. Just imagine the beginning of the reaction. You have a high excess of acetone and of your PNP, no product at all. So that means the few molecules will not form a dimer. They will always react with the acetone to make this, so that there is a directionality.
As long as they do something quickly to preserve that initial non-racemic state because of the absence of enough molecules. So it's a beautiful, beautiful thing. It's just like you know what the rate. You know what this is? This is the stirrer in the sodium chlorate system.
The sodium chloride system is totally different.
I know it's a mechanistically different,
It's
but
completely different.
I understand.
That people also don't consider that all these crystals are piezoelectric. Which also affects
Let's get drunk now, or?
Very nice. Congratulations. Good. That's it. Nice.
No, I mean, we have to confirm that. Give the credit to her.
By the way, I want to tell you guys something. In the United States, it would be illegal to have the kind of talking that has gone on here. You'd never hear it in fact, it's not even illegal. No one does it anymore.
Why not?
You never mention in a woman scientist her good looks or bad looks.
No. This was your expectation, but this was not my saying. You documented it.
Constant talk like that here.
I just said even more beautiful.
You are Neanderthal. You are behind the times. Yeah.